Here's gymnast Nellie Newton, our conceptual physics mascot. She's hanging out in the school gym illustrating the equilibrium rule that forces balance out to zero for objects held at rest. Nellie has a smile on her face. Why? Because she's learning physics and therefore enjoying herself. Don't we all enjoy ourselves when we learn things that we thought were over our heads? The downward force on Nellie is 300 newtons, her weight. Oh, I hope you can see that red vector against her magenta dress. Darn. Anyway, she grips the metal ring that's attached to a rope that goes up to the ceiling. What's the tension in the rope? It's got to be 300 newtons. Some of the two forces on Nellie balance to zero. She's in equilibrium. Suppose two vertical strands of rope support her equally. Then each strand has a tension of half her weight, 150 newtons, acting upward. Again, the vector sum of the forces equals zero. Ropes aren't vertical. Suppose they form an angle. Here's where a nifty rule for finding the resultant of a pair comes in. The parallelogram rule. A few words about parallelograms. A parallelogram is a four-sided figure wherein opposite sides are parallel. Such can be a square or a rectangle, special cases where all four angles are 90 degrees. We show pairs of vectors. The diagonal of the parallelogram represents the resultant of the two vectors. For parallelograms of other angles. Experiments show that in each case, the diagonal of the parallelogram represents the resultant of the vector pair. Now back to Nellie, who hangs by ropes at an angle to the vertical. Since she's in equilibrium, we know the rope vectors must vectorially add up to 300 newtons to balance Nellie's weight. That's this upward dashed vector, which will be the diagonal of the constructed parallelogram. We construct sides of the parallelogram defined by the angles of the two ropes. We're careful to draw the dotted lines parallel to the opposite ropes. Important. The constructed vectors show the magnitudes and directions of the rope tensions. So the resultant of this pair of rope tensions is 300 newtons up, exactly equaling the downward 300 newtons on Nellie due to gravity. The forces add to zero, and Nellie is in equilibrium. An interesting case occurs when the pairs of ropes are 60 degrees from the vertical. That's when the angle between them is 120 degrees. For this special case, tension in each rope is equal to 300 newtons, the weight of Nellie. What if the ropes form different angles? Then rope tensions will be different. In which rope will the tension be greater? Note this time the parallelogram has a different shape, with one side longer than the other. Here we see tension is greater in the right-hand rope. Rope tensions can be greater than the weight they support when the angles to the vertical go beyond 60 degrees. Consider ropes making this large angle. We see that the vectors are appreciably greater than the 300 Newton vector representing Nellie's weight. Got all this? I hope so. I want to leave you with a question. Suppose we replace this right-hand rope with a shorter rope with a much steeper angle. Does rope tension in the longer left-hand rope increase, decrease, or remain the same? Can you defend your answer? Until next time, good energy.